Hello, welcome to the course PH6B13E Computational Physics. The contents of today's lecture is taken from Numerical Method for Scientists and Engineers by K. Shankar Rao. In today's class, we will start our discussion on Module 2, Numerical Methods in Physics. The mathematical techniques we use for solving various problems, they can be broadly classified into two: analytical methods and numerical methods. And what's the difference between these two? By the way, whatever mathematical techniques you have learned so far in your various mathematics courses, like integration, differentiation, solving a differential equation, or finding the roots of a quadratic equation, and all these are analytical methods. Now I can illustrate the difference between these two methods with a simple example. So find the root of the equation f of x equal to x minus 5. And you know the meaning of root of an equation, right? You have to find the value of x for which f of x equal to 0. First one, analytical method. Here you equate the equation to 0. So you write x minus 5 equal to 0, from which you can find out the value of x equal to 5. This is simple and straightforward for this particular case. Now, what is numerical method? So here you start with an initial guess. Okay, so you assume that the value of x is something, okay, or the value of the root is something. Okay, so I start with an initial guess of 1. Okay, now I have to see whether this is the actual root. How do I find that? Basically substitute for x in this particular equation and find out what is the value of f of x. Okay, so f of 1 is going to be 1 minus 5, which is minus 4. Okay, so if 1 was the root, I should get the answer 0 here. So now I know that 1 is not the actual root. Okay, so I go to another initial guess. Okay, I give some other value to x. Let me say x equal to 6. Now I'm going to check whether 6 is the actual root. So f of 6 equal to 6 minus 5, which is 1. So once again, this is not the actual root. But if you notice here, f of 1 is negative, f of 6 is positive, which means somewhere in between these two, I should be able to find the actual root for which f of the function value is going to be 0. Okay. So from this initial guess, now I know that the answer, the actual root is between 1 and 6. Okay. Now, how do you arrive at the actual root? Now, one of the methods is known as the bisection method. So here I am going to choose the midpoint of these two values, or I am going to bisect this range. So my new guess is going to be the average of these two, that is 1 plus 6 divided by 2, which is 3.5. Now let me check whether 3.5 is the actual root. So I find the value of f of 3.5, which is 3.5 minus 5, which is minus 1.5. Now if you compare f of 1 and f of 3.5, in the case of f of 1, your answer is minus 4, which is far away from 0. On the other hand, in the case of f of 3.5, this is minus 1.5, which is closer to 0. In other words, your approximation or your guess is becoming better, right? So 3.5 is a much better guess compared to 1. So once again, if you look at these two, f of 6 is positive, f of 3.5 is negative, which means the actual answer is between 3.5 and 6. So see, you started with a wider range, now you are narrowing down your range. Okay. Once again, you have to improve upon your guess. What you do, you bisect this range or find the midpoint or average. So average of 3.5 and 6 is 4.75. This is your new guess. Okay. Now you calculate f of 4.75. So this is 4.75 minus 5, which is minus 0.25. So this is even closer to 0, right? So 4.75 is a much better guess compared to 3.5. So you keep repeating this. So initially you started with two guesses, 1 and 6. Then you narrowed down your range. So now you have got a new guess 3.5. Then you improve that guess, you reach 4.5. You can see that in each step or in each iteration, you're moving closer and closer to the actual root 5. Okay. So at the end of 5 or 10 iteration, you will be able to reach 5. But the one fundamental difference between these two methods is that in the case of analytical method, you get an exact solution. See, here you get an exact value, x equal to 5. But in the case of numerical method, you will never reach the exact value 5. You will reach a value which is very close to 5, like 4.99999, something like that. You will never reach the exact value 5. In that way, numerical method will give you an approximate solution, not an exact solution. Okay. Now let's try to understand some of the characteristics, features, or some of the basic differences between these two methods. As I said earlier, analytical methods give you exact solutions. On the other hand, numerical methods give you approximate solutions. In analytical methods, we use exact theorems to present formulas that can be used to arrive at exact solutions. On the other hand, in numerical methods, we use algorithms or step-by-step procedures to arrive at numerical solution. Here you have a step-by-step procedure, like you start with two initial guesses, then you bisect the range, find the new guess, keep improving that. So it's easy to implement in a computer program. Analytical method, it's difficult to implement in computational platforms. On the other hand, numerical methods, since it follows a routine, it follows an iterative procedure, it's much more easier to write an algorithm and implement in a computational platform. Analytical methods in general are more time consuming, and in some cases it's even impossible to find the exact solution. Now if you look at our example, this may not give you a correct picture, because in this case you got the analytical solution very easily. On the other hand, for numerical solution you have to do a lot of steps, right? But this is a very simple function. X minus 5 is a very simple function. On the other hand, if I throw you a function like f of x equal to x to the power 6 minus 4x to the power 5 plus sine x plus e to the power x square minus 1 by x, some random function, and I ask you to find the solution analytically, it's going to take you a lot of time. On the other hand, numerical method, this is less time consuming. Why do I say that? Because if you look here, there are so many steps involved here. But remember, when you write a computer program for this procedure, your computer operates at very high speed, like gigahertz of processing speed. So they can perform a large number of computation in 1 second. So even if the numerical methods take 100 or 1000 steps to arrive at the correct answer, for a computer operating in gigahertz processing speed, this is going to take 1 second or less than 1 second. So it is less time consuming because we are going to execute numerical methods usually with the help of computer programs. And mostly in all cases, it is possible to find numerical solutions, unlike analytical solutions. But since analytical methods give exact solutions, they are considered to be a stronger solution, and numerical solutions are considered to be weaker solutions. So generally we don't consider numerical solutions as proof of new ideas. Nevertheless, numerical methods are very important, because in many physical problems, since the problem is very complex, it's difficult to find the analytical solution. For example, if you want to find the electronic properties of a material. So what do? You take an atom and solve the Schrodinger wave equation, and if you have a one electron system like hydrogen atom, it's possible to find an analytical solution. But if you just scale up the problem to the next level, like a two electron system like helium, it's very difficult to find an analytical solution for the Schrodinger wave equation. Now imagine you have a system consisting of crores and crores of atoms, each atom having large number of electrons, and for each electron you will have to solve the Schrodinger wave equation. Analytically, this is an impossible task. In such cases, numerical methods will help you. So in physics, there are large number of numerical techniques for various problems, like finding the electronic band structure, finding the molecular properties, etc. And some of the names include DFT method or density functional theory method. Then you have Monte Carlo methods, ab initio calculation, etc. So all these are various numerical techniques which we frequently use in theoretical physics. Now in this module we are going to familiarize with a few simple numerical methods like numerical integration, numerical differentiation, extrapolation, interpolation, curve fitting, etc. So to start with, we will look into Taylor series expansion. Probably you are familiar with Taylor series from your mathematics courses. So you have a function y. Y is a function of x, and you want to find the value of the function at a given point x, and this value is unknown. On the other hand, the value of the function at a point x naught is known. So basically you want to arrive at the value of the function at x using the known value of the function at the point x naught. So you try to represent y of x as an infinite series. This is known as Taylor series, and this kind of an expansion is known as Taylor series expansion. So I can write y of x equal to y of x naught plus x minus x naught y prime of x naught, where y prime is the first derivative. This is dy by dx at x equal to x naught, plus x minus x naught squared divided by 2 factorial y double prime x naught, where y double prime is the second derivative, d square y by dx square at x equal to x naught, plus x minus x naught whole cube divided by 3 factorial y triple prime x naught, plus all the way to infinity. Now one important point you have to remember is that for this kind of a series expansion, x naught should be very close to x. Okay. Now even though this is an infinite series, when you are actually writing a program or when you are trying to find a solution numerically, you do not have to consider all these infinite terms. Why? Because as I said, x naught is very close to x, so x minus x naught is a very small quantity. For example, let me say this is 0.1. So in the first term I have the value 0.1 here. In the second term I have 0.1 square, which is 0.001, which is smaller than 0.1. In the third term I have 0.1 cube, which is 0.001, which is even smaller, right? Okay. So when you go into all the higher order terms, the value of the term is going to be very small, or the weightage of the term is going to be very small. So for all practical purpose, you can stop with first 5 or 10 terms or first 10 or 20 terms, because even though you have all other higher order terms, when you look at the magnitude of all those terms, it's going to be very small. At the end of the day, they are not going to improve the accuracy of your solution. So when you write a computer program for this kind of a numerical problem, you can consider only the first 10 or 20 terms and stop with that. Now let's do a Taylor series expansion for two common functions, cos x and sin x. So here we are going to do the expansion about the point x naught equal to 0. First let's find the Taylor series for cos x. Okay. So here y of x equal to cos x and x naught equal to 0. So follow this definition. Now I can write cos x equal to y of x naught, which is cos 0 plus x minus x naught. This is x minus 0 y prime of x naught. Derivative of cos x is minus sin x and x naught is 0, so you have minus sin 0 plus x minus x naught square, which is x minus 0 square divided by 2 factorial and y double prime of x naught. So derivative of minus sine is minus cos, so you have minus cos 0 plus x minus x naught cube, which is x minus 0 cube divided by 3 factorial y triple prime of x naught. So derivative of minus cos, this is going to be plus sine, so you have plus sine 0 here, and the next term is going to be x minus x naught to the power 4, which is x minus 0 to the power 4 divided by 4 factorial, the fourth order derivative, so that's going to be cos 0 here. Okay. Cos 0 equal to 1, so 1 minus sine 0 equal to 0, so second term is 0, minus x square divided by 2 factorial, once again cos 0 equal to 1, and the next term there is a sine 0 term, so that term goes to 0, and the next term is going to be 0, and the next term is going to be x to the power 6 divided by 6 factorial. Okay. So here if you notice, you have only the even power terms and all the odd power terms vanish, so you have cos x equal to 1 minus x squared divided by 2 factorial plus x to the power 4 divided by 4 factorial minus x to the power 6 divided by 6 factorial all the way to infinity. So cos x, the Taylor series expansion for cosine function contains only the even terms. Let's quickly write a Python program for this. So basically you have to create a series containing even terms. Now one thing you have to remember is that when you write a Taylor series expansion for trigonometric function, x has to be in the unit of radians, not in degrees. Okay. So let's write the program. Since we are using a factorial function which is part of the math module, let's first load the math module. So I say from math import star. So all the mathematical functions are imported. Now usually when we take angle as input, we input it in terms of degrees. Okay, so let's input the angle in degrees. So I say deg equal to float input, enter the angle in degrees. I'm going to input it as a floating number. As I said, Taylor series works only for radians. So once I input the angle in terms of degrees, I need to convert it into radians, which I do by multiplying it with pi and then dividing it with 180. Right? So x equal to deg into 3.14 divided by 180. So x is the angle in radians now. Now cosine series start with value 1, so I'm going to initialize cos x equal to 1. Now I need to decide the number of terms, so I can choose a safe number like 50. Okay, so I'm going to initiate a for loop with 50 terms. So for I in range 1 to 50, then I need to have only the even terms, right? So I'm going to create a variable known as e1, which is equal to 2 into I. Okay, so this will give me an even term. Then inside the for loop, I need to now create this. I need to create this infinite series now. Okay. So it starts with value 1, which I call as cos x. So cos x equal to cos x plus, then look at the terms here. I have alternate plus and minus terms. So how do I create alternate plus and minus term? I will say minus 1 to the power I. Right. So here I starts with value 1 minus 1 to the power 1, which will give you a minus sign here. Then in the second iteration, I equal to 2 minus 1 to the power 2 is plus, so I have plus here. In the next iteration, I is an odd number, so minus 1 to the power I will give me a minus sign here. So you have alternate plus and minus sign here. So that is taken care by the first term. Then you have x to the power even terms. So that is given by x to the power even divided by factorial of all the even terms. That is factorial even. So you do it for 50 iterations. You have 50 terms here. And after that, you print the value of cos x. So print cos degree equal to cos x. Now if you give the value of the angle as 0, so 0 degree is nothing but 0 radians. So when you do this iteration, you get cos 0 equal to 1. Okay. This is simple and straightforward. Next, same thing we can do for sin x. So once again, write on the Taylor series expansion for sin x. X not equal to 0. So y of x naught equal to sine 0, then x minus x naught, that is x minus 0. Derivative of sine is cos, so you have plus cos 0, plus x minus 0 square divided by 2 factorial y double prime of x naught. Derivative of cos is minus sine, so you have minus sine 0 and all the higher order terms. So this is going to be sine 0 equal to 0 plus cos 0 equal to 1, so x minus 0 equal to x, so second term is x. In third term you have sine 0, so third term becomes 0, and fourth term is minus x cubed by 3 factorial. The fifth term is 0, and the sixth term is x to the power 5 divided by 5 factorial all the way to infinity. So sin x equal to x minus x cubed by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 divided by 7 factorial. You can quickly compare this with the Taylor series of cos x, and you will find that in the case of cos function you have only the even power terms, whereas in the case of sine function you have only the odd power terms. So this is the fundamental difference between these two Taylor series. Since we know the Python program for cos function, it's very easy to write the Python program for sine function. So you start with importing all the math functions, then you input the angle in degrees, you convert that into radians. Now you need to initialize your series. Here the first value is x, so you initialize that sin x equal to x. Once again you consider the first 50 terms. Then here you are dealing with the odd terms, so you define odd as 2 into I plus 1. Now you write the series sin x equal to sin x. You need to have alternate plus and minus terms, that is given by minus 1 to the power I, then x to the power odd divided by factorial odd. So instead of even in the previous case, you have odd here. After that you print the value. Now one thing you have to remember, I have used a number of brackets here. This is particularly important when you are dealing with expressions containing large number of terms. So you can use brackets to segregate the terms. This will improve the readability of your code. Also, the chances of errors are less here. Okay. Now you can give various values to your degree and see whether you are getting the correct answer, because that's important. Once you do a program, right, you should see whether you are getting the desired result. Okay. So when I give angle as 0, I know the value of sine 0 and see whether you are getting the answer. So you will get sine 0 equal to 0. Then you give the value 90, sine 90 equal to 1. That also you get. Now you give another value like 30, sine 30 equal to 0.5. So actually you are expecting the answer to be 0.5, but in this program, if you give the input as 30, you don't get 0.5, instead you get 0.999994, something like this. And why it is so? Because numerical methods give you an approximate solution, not the exact solution. So in these two cases, it happened to be the exact solution, but here you can clearly see the difference between analytical solution and numerical solution. You will get a value very close to 0.5, but not exactly 0.5. You can also check the influence of the number of terms or influence of step size here. So for the case of 30, you can choose different number of terms. Okay, you start with 2 terms. So basically in this function you gave a range 1 to 2. Okay, so already you have the first term here. The range function will give you the second term. So basically your sine function will have the first 2 terms, x minus x cubed by 3 factorial. So with these 2 terms you can calculate the value of sine x. So that's, you get some value. Then find the difference between your result and the actual value, which is 0.5, and the difference is going to be your error. So if you get the exact value 0.5, the error is going to be 0, right? So here when you have 2 terms, the error is going to be 3.25 into 10 to the power minus 4, which is very small. Okay. Now you increase the number of terms. You include 5 terms. So basically you have range 1 to 5. So if you look at the series expansion, you are going to have the first 5 terms. Okay. Now you get a particular solution and find the difference between the exact solution and this numerical solution. This is going to be minus 2.03 into 10 to the power minus 11, which is very, very small. So you look at the error. When you have 2 terms, error is 10 to the power minus 4. When you have 5 terms, error is even smaller. Next, you include the first 10 terms. You will find that the error has decreased even for 10 to the power minus 17. So that's what I said. When you increase the number of terms, your approximation is going to become better and better. So usually we choose the first 10 terms. Now you can cross check this. You can write this program and do it for 20 iteration or 30 iteration, 40 iteration, 50 iteration. You will find that the value of the error doesn't change much after the 10th term. So even if you include 50 terms, the error is going to be of the order of 10 to the power 17 on. That's why I said, even though this is an infinite series, for all practical purpose, you can stop with the first 10 terms, because after that, the weightage of the higher order terms are very, very small. So even if you include all of them, the accuracy of your solution is not going to increase any further. Okay. So when you do programs in your practical exams, you can include the first 10 terms or first 20 terms. That's more than sufficient. So you can do as an assignment. So I have shown this table for the sine function. For the cosine function, you can create a similar table and see how close you are reaching to the exact solution. So that's about Taylor series expansion. In the next class, we will see another important numerical method known as curve fitting. Stay tuned for that. Thank you.